Hello, this is Jusop Choi from Sungkyunkwan University in Korea. At this time, I'll present ACIDroid, a practical app cache integrity protection system on AnDroid runtime. This work has collaborated with Sulin Kim, Junsung Cho, Kuja Kim, Seok Hong, and Professor Hyung-Shik Kim. This work is sponsored by Samsung Research. From the title of the talk, you might wonder why we need new integrity protection. In short word, AnDroid provides a new file format, and the file lacks prevention from modifying. Let me give you a detailed story. As you know, the not allowed modification of apps has been a topic of mobile application developing area. The app developers try to prevent the modification of their application, while the attackers try to modify them. Because the modified app seems to the original in appearance, the user installs the app with no doubt. It makes the attacker obtain the user's personal information. To prevent the not allowed modification, the developers have checked the integrity of the APK file of the application. For example, banking apps have a self-defense mechanism to check the integrity of their APK file through code signing. However, the integrity of APK files is not sufficient in the latest AnDroid apps. The AnDroid introduces a new feature called App Cache, to enhance the app execution performance. To treat the conventional security mechanism, the attacker can tamper the app cache file to modify the behaviors of an app. Because this attack does not change the APK file, conventional APK integrity checking methods are not helpful to prevent this type of attack. This is an example of an app cache tampering attack. We implemented a simple application that shows the word "Hello World." To modify the app cache file, we access the device using the ADB tool. And then, we copy the app cache file to the SD card. The path of the app cache file places two more folders from the APK file. And then, we extract the app cache file from the device. We open the app cache file using the hex editor. Find the text "Hello World," and then change the text into "Bye Bye World." We save the modified app cache file. And then, we push the modified file into the device using the ADB tool. In the final step, we replace the original app cache file with the modified file. As a result, as you can see, the application displays the text "Bye Bye World," not "Hello World." We can successfully change the app cache file. Before protecting an app cache file, we introduce the file in brief. The app cache file is a new file format suggested for improving the speed and battery usage. When the application is installed, AnDroid optimizes the DEX file into ODEX and VDEX files by the DEX2OAT compiler. Using these files, AnDroid executes the application. For improving performance, AnDroid optimizes DEX files. For example, if the DEX OP code is like this, the OP code is changed to the optimized OP code, and the parameter field is changed to the vtable field. The optimized OP code is decided by the optimization option, while the vtable is determined by the type of physical device. For example, in the Galaxy, the vtable value can be 1, while in the Pixel, the vtable value can be 2. And according to the optimization option, the optimization method of the app cache file is different. AnDroid version 7 and 8 have 12 and 10 compile filters, respectively. For example, with the verify filter, AnDroid only runs DEX code verification. With Quicken Filter, AnDroid runs DEX code verification and optimizes some DEX instructions to get better interpreter performance. The app cache files generated from different filters could have different hash values. Does only compile filter affect the app cache file? The answer is no. Even though the compile filter is the same, the generated app cache file could be different. Let's assume that we install an application, Instagram, in both Galaxy and Pixel phone. These two smartphones have the Quicken filter as the compile filter. However, the generated app cache files in these smartphones are different because the table values are different from each phone. Therefore, we have to solve this challenge that the app cache files, generated from the same app, are different with each type of physical device, AnDroid versions, and the optimization options. There was a trial to solve this problem. Wan et al. Suggested a method for protecting the integrity of an app cache file with a pre-computed hash value. Before the target APK is released, they generate app cache files with diverse compile filters and instruction types. And then, they calculate all hash values from all combination which can be occurred. They generate a secure store with the hashed values and concatenate the store with the target APK file. In this method, additional storage is needed. The secure store can occur the storage overhead. The overhead can be calculated like this. N_inst is the number of target devices, which is similar to the instruction set. N_compile is the number of compile filters. N_dex is the number of DEX files in the target application. The number 1 is to show the compile filter, and the number 4 is the size of the hash value. If an app having 2 DEX files wants to be installed in the ARM64 device, and the device only provides 10 compile filters, the size of needed storage is at least 90 bytes. With this method, the app cache file can be checked the integrity. However, this has a storage problem because the storage overhead will be increased with the number of cache file types. Let me show you our contributions. We designed a practical app cache integrity protection system on AnDroid runtime, named ACIDroid. And, we evaluated ACIDroid's performance against app cache tampering attacks on 11 popularly used real-world AnDroid apps. Our system achieved 155 milliseconds verification time overhead. The storage overhead is 80 bytes, and this is smaller than the existing methodology, about 28.9 times. This is our proposed system. Our system has 4 components: event listener, hash register, verifier, and updater. The system is worked in a rich execution environment, such as AnDroid. And we also calculate the hash from the app cache file and store it in a trusted execution environment, such as Trust Zone. I will explain each component in detail. The first component is an event listener. When the application is installed or updated, AnDroid executes the DEX20AT compiler to generate the app cache file. Our first component, event listener, catch the signal of DEX20AT to handle the following actions among the hash register, verifier, and updater. The second component is a hash register. This component is executed when the application is installed. Hash register calculates the hash value of the app cache file. It then stores the hash value into secure storage such as trusted execution environment. The hash value of the app cache file is securely protected by the trusted execution environment and can be accessed by our system. The third component is a verifier. When executing an application, the zygote process approaches the application. The action of the zygote is handled by the event listener. The verifier checks the integrity of the app cache file, calculates the hash value of it from the app storage, and brings the stored hash value. If the calculated hash value is the same as the stored hash value, ACIDroid lets the application continue to run. If the hash values are not the same, ACIDroid kills the application, because the different hash means the app cache file is modified. The last component is an updater. This component is executed when the application is updated. If the application is updated, the dex20at compiler is executed again, so the app cache file is changed. Therefore, ACIDroid calculates the hash value of the updated app cache file, and then stores the new value into the trusted execution environment after encryption, as well as removing the old hash value. To evaluate our system, like this table, we collected 11 popularly used AnDroid apps from 7 categories. The apps are sensitive to the modification of the control flow. To test the modification of the real-world applications, we implemented our proposal with like following. ACIDroid was implemented in Java application, not in the kernel. Our system is more effective in the AnDroid kernel, so in future work, we will insert ACIDroid to the AnDroid open source project. To check the integrity, we use the hash algorithm as SAC256. The hash values are stored in an encrypted form in a trusted execution environment. This is our environments for experiments. We tested 7 environments on 3 different AnDroid versions as follows. The AOSP installed computer had Intel Core i7, 16 GB memory, and GeForce GTX 1080 graphics card. We give the AOSP environments with 4 multi-core CPUs and 1536 MB memory. This is our experiment result. We measure the time overhead at 3 phases: installation phase, verification phase of the benign apps, and verification phase of the modified apps. To measure the overhead time ratio at the installation phase, we measure the time t-regist, which the system spends on registration, and the time t-install is that the app takes to finish the installation. To measure the overhead time ratio at the verification phase of the benign and modified apps, we measure the time t-verify, which the system spends on verification, and the time t-ready is that the app takes to reach the ready state from the start state. The time overhead has a little bit of a wide gap. For example, the verification time overhead of Outlook is lower than the time of Dropbox. This is because the ready time of Dropbox is faster than Outlook. This is also the reason why the hash value registration time overheads of Outlook and Dropbox are very similar. The time overhead in the Pixel phone is slower than the time in the AnDroid open source project. This is because the Pixel phone uses physical storage. However, the AnDroid open source project does not have the actual storage. Therefore, the access time to the physical storage might be huge, and this makes the time overhead slower. The storage overhead is shown in this table. We calculated the storage overhead of Wan et al.'s method. We assume that the application is the booking app, which has 8 X files. AnDroid is version 8, which has 10 compile filters. And last, the target devices are 7 instruction sets. Using the equation, we obtain the storage overhead as 2310 bytes. On the other hand, our system needs 80 bytes only. We reduce the storage overhead by almost 28.9 times. Let me show you our conclusions. We proposed ACIDroid, which is a practical app cache integrity protection system for checking the integrity of app cache files via the secure management of hash values for app cache files on trusted execution environment. We implemented a prototype and evaluated the performance of ACIDroid with 11 real-world apps running on several AnDroid versions on AOSP and Pixel 2, respectively. Thank you for listening.